I was working at SRI with Mike McCubry, and we were working on the palladium system, palladium hydrogen system, as a way to measure the amount of hydrogen dissolved in primary coolant in nuclear reactors. And on the day that the announcement was made, 30 years ago yesterday, we were testing, and Mike in particular was testing our device by passing current through palladium, actually dissolved in heavy water, because he was testing it up in Canada where their reactors use heavy water. And so Mike knew both Martin and Stan, and he decided, okay, if these guys say it, then there must be something worth looking at here. And we asked our contract monitor, who at the time was Tom Passel at the Electric Power Research Institute, if we could divert a few months and not a whole lot of money, and had a serious underestimate of how long it would take to prove or disprove this. But we were fortunate enough that our first experiment showed something very encouraging. Well, I'd been doing electrochemistry for a number of years then, and electrochemistry is not easy. And one of the things we learned very early was Martin said it was easy. And unless you'd been doing electrochemistry for at least a few years, there are a lot of technical aspects of it that you needed to bring to bear. And if you'd never done it before, chances are you were going to get it wrong. Well, within SRI, it was very encouraging. In fact, of course, in the early days, the interactions were positive, which pretty much with everybody, because there are always new technologies or discoveries being made, and until they're proven or disproven or ignored, everybody is interested to jump on it. I was fortunate enough to be at SRI when the high temperature superconductor had started a couple of years earlier, and it was interesting to see how that grew across the field, across the world. That one became so easy that there were high school students doing it within a year, which of course contrasted with cold fusion, which was still very difficult to do, 30 years later. I think it's everywhere. I think so many people have that instantaneous gratitude that they figure if it hasn't been done in X number of years, or even sometimes X number of months, it's either wrong or it's so difficult that it's not worth me spending my time and my career working on it. And I've said before, when you work on anything in science, if you're not at the forefront of it, it's going to negatively affect your career, even if it isn't a controversial subject. I think it's going to take a lot of expensive study of the nuclear mechanism, or the nuclear products that don't exist and those that can exist. And in particular, working with the Brillouin, they have a hypothesis, and that hypothesis includes, if you get to a certain stage and use a certain set of parameters, you should see tritium, for example. And so if you could get a physicist, an experimental physicist, to go in there and reproduce that and do what they're told, and maybe play with it and play with the parameters until they do see the tritium, turn it on, turn it off, I think that will start well, I don't know about the plasma physicist, but that will start the majority of the physics community to say, okay, there's new science here that we don't understand. Well, there are two extremes. Of course, as a scientist, new science always teaches you something that you don't expect. And so that could lead to 1,000 things that you can't even imagine today. But on the other hand, of course, most of the experimentalists are looking at heat and even direct electricity generation. So energy in general is so important to the planet these days that this can contribute or become the major contributor to solving the energy crisis. Well, heat itself, as they've shown in the last day or so, you can go with Stirling engines or thermoelectric, or if you have a large amount of high quality heat, you can use steam generators. And one of the concepts that you can do is there are all these stranded assets, as they refer to the coal-powered fire plants. You could replace that coal boiler with a cold fusion boiler or whatever. It was actually like a normal conference. That was very interesting. It was interesting to go meet the people and to take a look at the diversity. The diversity was amazing. As you know, today, I'm working mostly with Brillouin, and they're not working with palladium. They're not working with heavy water. They're not working with any liquids. But that was just a small part of it. There were people all over the field. But it was a regular conference. I have one memory from the early days. We worked a lot with the Electric Power Research Institute, and we'd go over there, and a number of scientists at EPRI were interested in it, and a number of them were funding different groups at the time. But I remember one of the meetings in the early days, we were over there with Tom Passel and a number of other scientists, and one of the other EPRI scientists asked a question as an analogy: is this 1909 or 1939? And what he was asking, of course, are we back where Rutherford just discovered the alpha particles, and we know we've got subatomic particles, and it's going to take half a century before we get anything useful out of it? Or is it the Chicago pile, where they finally started seeing powered heat generation from a nuclear reaction? And it was only 20 years to the first commercial reactor in the US actually came on, and like that. Well, as we stand here 30 years later, you know, we really hope that we were a lot closer to 1939 than we were to 1909. Well, Martin, of course, was always the professor, and that was part of the problem early on. He never really wanted to teach or to show you point by point how you had to do this. He didn't want to have a black box, because that's not how professors teach. He wanted you to figure it out, to learn, to really think about it. And I think that was part of the problem in the early days, where people couldn't get it right because they didn't spend the time to do their homework and figure out what's the right way to do this. And they didn't want to spend the time to figure it out themselves. Why we're here, this is a great conference. I'm really disappointed that I haven't come to more of them. I've only been here once before. Mitchell puts together a really great group of scientists and engineers, and I'm happy to be part of it. And he and Gail do just a great job to put this together and make it work. And having helped put a conference together back in ICCF4, it's a monstrous, thankless job. Oh, absolutely. I saw that in the rest of my work at SRI. I happened to have the unfortunate circumstance to have 4 people under the age of 40 leave our group over 18 months, and it just decimates the group. And same thing here. If you can't bring them in, You can't bring young people, particularly graduate students, and that's the worst part. But I am encouraged that I see a couple of young people, a couple of new faces. And one of the things I'm most encouraged about is the system that Pam Boss is putting together, where she's working with students at UCSD, starting with the undergraduates. And that's being funded partially by the Anthropocene Institute. And that's important. The people who are here who are funding different groups, and there are people here who are looking to fund different groups. That's always an interesting part to learn about at these conferences. Well, yes, some of it is that we are early on, and probably still today, this should be a National Science Foundation project or Department of Energy, what they used to call their Basic Energy Sciences Group project, and none of those have ever shown any interest in this group. So there's very little money being put in by the large government institutions to do the fundamental science. But back to the question of capital cost, we had a proposal back in the early 90s to EPRI to expand it just to look at the material science. And I think the proposal was about $25 million. And the material scientist over there who read it said, I can't fund this because there isn't enough money to solve the problem. People don't appreciate it. The scientific method is great and it works maybe 10 to 30% of the time, but probably 70% of the inventions and discoveries that become practical are put together empirically and then later on understood, or not. As we heard in this conference, there are a number of things that are used every day that have been around for almost 100 years that aren't well understood. These days, I'm excited about the breadth that there are people understanding or trying to understand the fundamentals. They don't have the money to look at the real problems, the fundamental, studying fundamental science, subatomic particles is a very expensive undertaking. And I don't know if this field is ever going to attract the wide view of science. It's almost a chicken and an egg. You need to be shown that you can do good fundamental science and good nuclear physics before someone's going to give you the ton of money you need to solve the problem. But I'm glad to hear there are a lot of people there. I think the theories are coming together. Boy, in the early days, the theories were all over the map. And the theorists, where you would argue with each other in very strong terms. It was very exciting to be standing in the room with, three of the theorists standing up and shouting at each other from across the room. But, we've matured. Physically and mentally and emotionally as a group. So I think I think it's helping us get better and closer to an answer. I haven't had that. I have to admit, there was a time from 2008 through 2011, there was a scientist who was part of the group who was able to put a very formal meeting at the American Chemical Society. And you heard about some of that this week or this weekend. And I happened to have the privilege to host one of those in 2011. And it was great to see a place like the American Chemical Society get interested. Even earlier, the Electrochemical Society was interested. We published in both the Electrochemical Society Journal and Electroanalytical Chemistry. So there was a time for about 2 or 3 years where you could publish in the peer-reviewed journals. And I have to really compliment Pam Boss and Stan Spock for getting and Larry Forsley, all those papers out in the peer-reviewed journals. And that makes a difference. I think I get interest. I have a ResearchGate account and LinkedIn, and I get people asking to follow me and join me from all fields of science just because of this field.
Great.
So I was going to say, I totally forgot. I looked at your face and I was like, oh, I went blind.
More about Anthropocene.
Oh, what does it feel like to be part of such a revolution in science? It doesn't happen very often, this kind of paradigm changing. Science.
It is, it's exciting, but like everything else, it's risky. You know, I just retired from the basic portion of my career and starting to move on. I want to see it going, but you know, it's kind of both sides there. It's paradoxical. It gives me the opportunity to do really interesting stuff without having a lot of the constraints of a formal institution. On the other hand, we're not getting any younger. I don't know how many more years I'll be able to work on the topic and hopefully see it to a fruitful conclusion.